Okay, let us return back to our problem solving the second order linear homogeneous differential equation. Recall that, consider again the second order homogeneous ODE of the form P of x y double prime plus Q of x y prime R of x y equal to 0, or in the usual reduced form, this can be taken as A2 of xy on dividing both sides, or there's Q over P y prime R over P y equal to 0. Okay? So with variable coefficients. Okay, the general solution is the combination of two linearly independent solutions, but unfortunately, as we stated in the part 1, there is no general procedure to find explicit closed form solutions. That is, a solution in terms of a finite combination of elementary functions. So instead, the idea is to find the power series representation of the solutions. Okay? So look, first of all, we say that we are looking for power series solutions about an ordinary point. So what is an ordinary point? Here is a definition. Okay? Let A1 of x and A2 of x be analytic in some x interval. So if A1 and A2 are analytic, you know that they are infinitely many times differentiable, and they are functions which are equal to the sum of their Taylor series about x0 or in some x interval, okay, or Q over P, R over P. Or let's first define the ordinary point in connection with this form, with the reduced form. Okay? So any point say this, some x interval, so x minus x0 smaller than rho. Okay? So any point on the interval or in the interval x0 minus rho, any point x, say, in this interval lying in the interval x0 plus rho is called an ordinary point of the differential equation y double prime plus a1 of x y prime a2 of x y is 0. Good. So recall that if there is the points on the other hand, the x values for which a1 of x or a2 of x or both are undefined. Of course, if there is any, are called singular points. Of the differential equation. So in other words, if a point x is not a singular point, and if it is a number where a1 and a2 are both analytic, then it is called an ordinary point of the differential equation. Okay? Now, sometimes, look, this definition is given. Note, the same definition, if we use that form, p of x y double prime plus q of x y prime plus r of x y equal to 0, then we define ordinary points of the ODE as follows. Good. Look, assume P, Q, and R are analytic. Okay? On some x interval. Now, the points, if there is any, of course, with this p of x0 equal to 0, or p of x equal to 0, the points x, or the values of x, okay? With this are called singular points. Of the ODE. Actually, if you write the equation in that form, y double prime, q of x, y prime, r of x, p of x, y equal to 0, okay? Because P, Q, and R are analytic. Now, at the roots or zeros of P of X, if there is any, okay? If there is any X making P of X 0, clearly this coefficient becomes undefined. This coefficient becomes undefined, okay? And therefore implies that the value of that X is a singular point of the differential equation. Otherwise, okay, P of X non-zero, if P of X is non-zero, the X values are all ordinary points. Okay? Now, the importance of defining an ordinary point are called ordinary points of the differential equation. So the importance of giving this classification is that let us use that form, y double prime plus a1 xy prime a2 xy is 0. Okay? The existence uniqueness theorem tells us that when you classify the singular points, when you find the singular points, you define several, one or more than one X interval in which a solution is sure to exist. Okay? And furthermore, if the coefficient functions are analytic at some X, which is called an ordinary point, we expect that the solution is also analytic, so it has a Taylor series representation. The solution can be taken as the sum of its Taylor series expansion. Okay? So we give the following theorem. Let's consider that y double prime plus a1 of x y prime a2 of x y is 0. Let x0 be an ordinary point. Where a1 and a2 are both analytic, then it is reasonable to think that y, okay, this is a combination of equation containing analytic functions. Okay, so y is also analytic, and therefore be an ordinary point. Then there exists a solution of the form an x minus x0 to power n. Okay? Which is look, this is the Taylor series representation of our solution about x0. So x0 is an ordinary point, so that we expect that a solution may be characterized as a representation in terms of its Taylor series expansion around or about x0. In other words, y of x, the required solution, is equal to the sum of its Taylor series. okay? Which is the Taylor series representation of a solution. Now, for some, of course, where rho is the radius of convergence of that Taylor series. Now, question 1. So this is true for as long as x0 is an ordinary point, we represent the solution as a power series like that, independent of a1 and a2. All we require is that a1 and a2 are analytic functions. Okay? So the procedure is straightforward for any second order ODE. But the question is, how can we find the coefficients? First question is that how can we evaluate the coefficients? Second, what is the radius of convergence of such a series solution? Okay? So, look, we can answer the two questions without any trouble. Actually, now first remark. How do we calculate AN, the coefficients we propose? So remember, we propose a series solution AN x minus x0 about an ordinary point x equal to x0. Then, how do we calculate the coefficients AN in this solution? Look, recall that if this series is the Taylor series of y, AN in principle is the nth derivative of y at x0 over n factorial. Good? For n1, 2, and so on. And when n is 0, a0 is y of x0. But y is the unknown solution of the differential equation. So we cannot calculate the coefficient using this formula, which is valid for the when y is known. If y is known, remember calculus courses, given a function, our objective was to calculate its Taylor series or Maclaurin series for a given function, which is analytic, okay, and has a Maclaurin series or Taylor series representation. So in calculus courses, y of x is known. Therefore, in principle, its derivatives are all known because it is infinitely many times differentiable. Okay, it is an analytic function. So these are calculated. Y is known. But here, y, so y of x, since y of x is the unknown solution of our ODE, we cannot use this formula, the formula yn x0 over n factorial for an. Yes? The reason is obvious. Y of x is unknown. It is this required solution of our differential equation. So we cannot calculate the coefficients by using the known formula for the Taylor series representation of a given function. Okay? But we'll see that, but instead we know that y must satisfy the differential equation. So we are going to use the ODE itself to calculate an, to be made explicit later. Okay? Now, second, what is the radius of convergence? Of such a solution, of such a power series solution. Of course, you may say that when you construct fully the power series solution, that is, when you calculate the coefficients, yes, you have a standard power series under consideration with known coefficients. Then you can apply any test known for power series, such as power ratio test or any other test, to find the radius of convergence. However, this is unnecessary, and without actually constructing this solution, without calculating an, it is possible to find the radius of convergence of the proposed power series solution. Here is the fact. You may say a theorem for this, estimating the radius of convergence. The power series solution about x equal to x0, okay, has a non-zero radius of convergence. That is, it is possible to find an x interval centered at x0 where rho is the distance from x0 to the nearest singular point to x0, if there is any. Okay? So this power series around x0 is convergent in this x interval, real x interval, with radius r, where rho, the radius of convergence, can be determined by inspecting the singular points of the differential equation and finding the singular point which is nearest to the point at x0. To this end, please be careful. Let us give some examples. Let's explain the situation, giving a specific example. So this theorem, although we didn't prove it rigorous, we didn't give a rigorous proof, may be justified using the existence uniqueness theorem or basic theorem for linear differential equations. Let us consider the examples. Let's say y double prime plus x y prime minus 2y is 0. Okay? So this is an equation with variable coefficients. There is no general procedure to find the two linearly independent solutions. Good. In closed form, in terms of a finite combination of elementary functions. Look, consider this equation. Now, where a1 of x is x, it is a polynomial which is analytic everywhere. a2 of x is minus 2. It is a constant function, analytic everywhere. Okay? Where a1 and a2 are clearly analytic functions. Everywhere for all x. So this equation has the ODE has no singular points. Has no singular point. Any point is an ordinary point. So, for simplicity, let's choose x0, which is an ordinary point. According to our first theorem, we propose a power series solution of that form, an x2 power n. Okay? So the solution is written as the sum of the Maclaurin series. Okay? So I don't know y of x, but I can calculate its Maclaurin series about the origin. Origin is an ordinary point. So what is the radius of convergence? x0 is 0. Okay. Yes. Let's choose x0, 0. Yes, that is 0 for simplicity. But any point can be taken as an ordinary point. Good. So we choose 0 particularly. And there is no singular point. The theorem tells us that the radius of convergence is something like that. And rho is determined by the nearest singular point. Good? But there is no singular point. No singular point at all. Okay, look. So here is x equal to x0. So the radius of convergence is bounded by the nearest singular point, but no singular point at all. Therefore, no singular point anywhere. Good. Therefore, rho is infinity. So rho is infinity because there is no singular point. Okay? So the radius of convergence of such a power series solution may be bounded by the distance from x0, here 0, to the nearest singular point. Since there is no singular point, okay, there is no bound for rho. So propose a power which is convergent. This is convergent. So y of x, this one a n x to the power n, will be convergent. For all x. Okay? That is so as you see, without making the series solution explicit, without calculating the coefficients, we see that such a power series representation of the solution should converge everywhere. Good? So it remains only to find an. And this is true for any other type of series solutions. Okay? Where we choose x0, not 0, and any other number. Okay? Every point is an ordinary point. So you can represent the solution as a power series around or about any point x0, and the resulting series solution has a radius of convergence which is infinity, since there is no singularity to give a bound on the radius of convergence. But it is important, an important remark is that complex singular points, if there is any, should be taken into account in finding rho, in finding the radius of convergence. Good. This is important. For example, look at this example. X squared plus 1 y double prime plus e to power x y prime plus sine x y is 0. Good? So we give the equation in the non-standard form. Okay? So coefficients are all analytic functions. Good. Sine x has a very well-known power series expansion. E to power x has a Taylor series representation. X squared plus 1 is a polynomial, so it is analytic. But look, or writing the equation in that form, in the reduced form, ex x squared plus 1 y prime sine x over x squared plus 1 y is 0, or let's choose the coefficient of y as so this is simply sin xy equal to 0. Okay? This is the reduced form. So first, no real singular points. But there is a complex singularity. But this number z plus or minus I, good, when x is this a complex singularity. Yes, if x is a complex number plus or minus I, then the coefficient of y prime becomes undefined. So there is a complex singularity. So in this case, look, in such a case, it is good to draw a picture. In determining the radius of convergence without calculating. So now, here is plus I, so this is 1 unit, and minus I, 1 unit, on imaginary x, real x. Good? So singular point. Okay? So if we choose x0 equal to 0, which is an ordinary point. So all real numbers are ordinary points. So if we choose that, then a solution is something like that, or Taylor series or Maclaurin series representation of the solution is that. And here is x0. So what is the theorem states that the radius of convergence, okay? So x should be smaller than rho. The radius of convergence is bounded by the nearest singular point to x0. And the nearest singular point is the singular point in the complex plane. In complex plane, here is 1 unit. The nearest singular point has distance 1 unit to x0. So rho is 1. Or more typically, sometimes it is better to write, to be more pedantic. Rho is at least 1, because sometimes the solutions may be reduced to polynomials, and therefore they converge for all x, but at least rho is 1. Okay? Often rho is 1, or it is at least 1. So without finding this solution, look, independent of the equation under consideration, we write the solution like that, about 0. Good? And we find the radius of convergence must be at least 1. So then it is a mechanical calculation to evaluate an to be introduced later. Okay? Or if you choose if we choose x0 as 1, again ordinary point, we have a solution of the type, a power series like that, an x minus 1 to power n. Good. With that, x minus 1 smaller than rho. This time, look at that. Now we choose x0 equal to 1. Good. So this distance to this singularity and this singularity are the same from symmetry. So this is rho. Okay? The nearest singular point to 1 is the singular point at I. So this distance, 1 unit. So this is, rho is 1 squared. So radical 2. Okay? So the distance from from x0 to the nearest singular point is radical 2. So where rho is radical 2 or larger than radical 2 in general. So we find the radius of convergence without knowing the series explicitly, without knowing an. Good? If, let me consider another situation. Example, let's consider that x squared plus 1 again. Good. X minus 4 or plus 4 y double prime. Good. Is 2y prime plus, or 2y, say just that, is 0. Okay? This is a second order ODE with variable coefficients. Or in the reduced form, one can write it as 2 over x squared plus 1, x plus 4, y is 0. So what about the singular points? What about the singular points? There is a real singular point at x equal to minus 4 where the coefficient is undefined, so it cannot be analytic. And singular points are complex pair of singular points plus or minus I. Good? So this time the equation has a pair of complex conjugate singular points and a real singular point. Therefore, let's consider this picture. Again, here I is a singular point, minus I is a singular point, and the point at x equal to minus 4 is a singular point. Good. This is real x, imaginary x, complex plane. So now, choose, for example, choose again x0, 0. Is it an ordinary point? Yes. x0, 0 is an ordinary point because it is not a singular point, so it is an ordinary point. At x equal to 0, this rational function is analytic. Okay? So ordinary point, the only singular points are located at minus 1 on the real axis and plus or minus I on imaginary axis. Okay? So there exists a solution. A solution is of the form. Look, the advantage of finding power series solutions of a differential equation is that it doesn't differ when we consider a different equation. Okay? For the previous equation, if you choose x0, 0, if it is an ordinary point, we are looking for a power series solution of the same time, independent of the differential equation under consideration. We propose a solution of that form. So what is important, as we know from the previous review about the power series, a power series makes sense whenever it is convergent. So this power series makes sense for all x where lying in this interval. We are interested in real solutions, so we consider real values. So in the previous example, look, if you want to write the interval, real x interval, we have this minus radical 2. Since we are interested in x minus 1, radical 2, okay? In the previous example, this is the real x interval we are interested in. Good? So, sorry, I return back to the previous example. If you consider the solution around about x equal to 1, which interval is the interval of convergence? Radius of convergence is radical 2. Radical 2 is somewhere. So 1 plus radical 2. So the x interval is that. Okay. And radius is radical 2. So 1 plus radical 2. Okay. So we are interested in that interval. And here, 1 minus radical 2. Radical 2 is larger than 1. So this is a negative number somewhere. Okay. 1 minus radical 2. So for any x, rho is radical 2. Rho is radical 2. So because we are interested in real solutions on a real x-axis, such a solution, a n x minus 1 to power n, which is a power series centered at 1, is convergent for all x in this interval. Okay? Now, we have this, and what is the singular point nearest to x0? In this, return back to our example, we choose x0 equal to 0. So this singular point at I has distance 1 from x0, or the distance between x0 and the singular point is 1 unit. Good. Therefore, rho is 1, or at least 1. Okay? So on the real line, so this solution will be valid. Here is 0, 1, 1 unit. So this is minus 1 and 1. So for this interval. Okay? So such a series solution is convergent, is guaranteed to converge from minus 1 up to 1. Good? But if you choose another ordinary point, if you would like to expand the solution, about any other ordinary point, such as if we choose, look, if we choose, for example, x equal to 2, x0 equal to 2. Okay? Now, the form of the solution, the power series solution is of the form please do not confuse. I use the same symbol for the coefficients an, but of course, in the expansion around 0, the coefficients of this series and the coefficients of this series are not the same. Just we use an as a symbol for the coefficient of the series. Of course, if you expand the solution around 2 or about 2, the coefficient will be different than the coefficient of the solution expanded about the origin. Good? But we use the same notation. For what? For, now, x minus 2 smallest than rho. And to find rho, we need to find the distance from 2 to the nearest singular point. Okay? So, from this picture, we see that here is 2. Here is a singular point at 4, at minus 4. Let's say minus 2. Let's choose minus 2. Sorry. So the solution is this form: x plus 2 to power n. So x plus 2 should be smaller than rho. Okay? So now these are singular points, minus I. So what is the distance from minus 2 to 1? Clearly, this is 2, 4 plus 1. Good. This is 1. This is 2. Okay? So radical 5. But when you consider this distance is 2 unit. Okay? So the nearest singularity nearest to x0 equal to minus 2 is the singularity at minus 4 with distance 2 units. So such a series solution, so this solution an x plus 2 to power n from 0 to infinity converges for x plus 2 smaller than 2. Okay? In the interval, in the real interval, this one, x is minus 2, radius of convergence is 2, so this is the point at the origin, and this is the nearest singular point, 2, so in this interval, from minus 4 up to 0. And this is in a good agreement with the statement of the existence uniqueness theorem. Remember, from existence uniqueness theorem, if we are interested in the real values of x, existence uniqueness theorem tells us that the solution is valid from existence uniqueness theorem from basic theorem, say, of linear ODEs, okay? A solution is sure to exist in what interval? Okay. There is a singularity at -4, or from -4 up to infinity. So look, the interval, the basic theory tells us that, so forget about this one, because we propose a solution around -2, which lies in this interval, okay? But the series solution is sure to converge from -4 up to 0, which is a sub-interval of this interval, suggested by the basic theory of linear differential equations. So -4, 0 is a subset of this interval. Okay? So this is the largest possible interval. If you find the solution analytically, okay, in terms of an elementary functions, in terms of a finite combination of elementary functions, it is sure that the solution will converge in this interval. Okay? But if you attempt to find the series representation of that solution about -2, it is guaranteed to converge only in this interval, which is a subset of that interval suggested by the general theory. Okay? So I hope that you understand that if we consider an ordinary point, the definition of an ordinary point is clear. We look at the coefficients of the differential equation, okay? So if we consider any point where the two coefficients are both analytic, then it is an ordinary point. So it is possible to construct a power series solution about that point. Good. And it is possible to estimate the radius of convergence of the proposed power series solution. The radius of convergence depends on x0 we choose, and also depends on the singular points of the differential equation. Okay? To be specific, the nearest singular point to x0 is important to give a bound for the radius of convergence. Okay? Now we know everything about that solution, which is independent of the differential equation under consideration, and which depends only on the point x0 we choose. Suggested that, or assume that, or suppose that x0 is an ordinary point. Okay? So all we need is to evaluate the coefficients a n. Okay? So we finish this lecture by giving an example. First of all, I give a trivial example in the sense that, look, let's write the example. So you understand why this problem is trivial. Find the power series solutions. Find the two. Find the power series representation of solutions of the ODE. Now this is trivial. Look, note. This is a trivial problem, since we already know that what is that? This is an equation with constant coefficient. So the characteristic equation, what is the characteristic equation? Lambda squared plus 1 is 0. So lambda is plus or minus I. So purely imaginary. So the solutions are cosine x and sine x. So this is C1 cos x plus C2 sine x. This is very well known. Okay? Is the general solution. So I mean that there is no need to use power series representation. The solution is a closed explicit solution in terms of elementary functions. Elementary functions of mathematical analysis are known. First solution is cosine x, second solution is sine x, and the combination gives us the general solution. But just to illustrate the procedure to find the coefficients in a proposed power series, we consider first this example, which is a trivial example. Now forget about this, or assume for a moment that cosine x and sine x are functions which have not been discovered yet. Okay? So if cosine x or sine x have not been discovered, of course, we couldn't write the solution in this form. So observe that. Look, the equation is an equation with constant coefficient, has constant coefficients, analytic everywhere, that is no singular point, so any point is an ordinary point. So choose particularly all points. So all x real are ordinary point. Okay? For simplicity, choose x0 equal to 0. Okay? And propose this. Y of x a n x to power n. Good? Since there is no singular point, so the distance from the nearest singular point to the origin is infinity. Okay? Of course, infinity is not a number, but there is no singular point to give a bound for the radius of convergence. So for this is convergent with rho infinity. Look, without finding the solution, we give the radius of convergence of the proposed power series solution, looking at the differential equation under consideration, and identifying its singular point. No singular point, so radius of convergence is infinite. Good? So, the only thing which remains now, we have to look for another differential equations. When we choose x0, 0, we propose a solution of the same type. Okay? So what is the difference? The difference are the coefficients. Okay? Which changes from one equation to another equation. Now, it remains only to determine the coefficients. The idea remains fixed. If this series is a solution, then it must satisfy the differential equation upon substitution. If y of x, yes, defined as the sum of its Maclaurin series is a solution, it must satisfy the ODE upon direct substitution. So find y prime. So thanks to the review, we know that the derivative of such a function can be made term by term. Therefore, y prime is from 1 n times a n x to power n minus 1. So I start the series from 1 because the first term, okay, look, always you consider the explicit form of this solution, which is something like that. a1x, a2x squared, an x to power n. This is always the case if we are expanding the solution about the origin. For every second order differential equation with any coefficient functions has a power series solution about 0, which is of this form. So only the coefficients are different or depends on the equation under consideration. So when you take the derivative term by term, the derivative of the first term is 0. So we can omit the first term and start the series for the derivative by 1. And similarly, y double prime, take one more derivative. Now, the term when n is 1 is a constant. So n minus 1 a n x to power n minus 2. We start the series from 2. This is the second derivative series. Now, let us substitute into the equation. So what if the proposed power series is indeed a solution? It must satisfy the differential equation. Okay? So recall again that we don't know y of x. Okay? For a moment, forget about cosine x and sine x. And we don't know the solution, so we cannot calculate the coefficients an using the formula given for a Taylor series, giving the coefficients of a Taylor series or the coefficient of a Maclaurin series in calculus course, in a standard calculus course. But we have the differential equation to satisfy. So substitution of y and y double prime into the ODE. Okay? What we have y double prime plus y So the series for the second derivative, n minus 1, a n x2 power n minus 2, plus the series, this is the series for y double prime, and this is the series for y, a n x2 power n, this is y, must be equal to 0. Okay? So the two series should be collected under one series to give a nice formula for the coefficient. So look, this is a series starting from n minus 2 and n, but we can use a shift, let's say n minus 2, n minus 2 is k, okay? Good. So when n starts from 2, k starts from 0 up to when n goes to infinity. So does k. Good. So y double prime plus y can be written as, with this index shifting, okay, we have k plus 2, k plus 1, a, n is k plus 2 times x2 power k plus this series, okay, from n0 up to infinity, a n x2 power n must be 0. And now k starts from 0 up to infinity. So the two power series have the same xk, xn. So because, again, k is a dummy variable or dummy index, okay, we write it in that form, k plus 2, k plus 1, or n. Let's use n. n plus 1, a n plus 2. Just for this series, k is interchanged by n. Okay, just the name of the counter or the symbol we use for the counter has been changed from k to n again. So we have x2 power n from 0 to infinity plus a n x2 power n must be 0. Okay, so the two power series with the common x2 power n, so which gives this n plus 1, n plus 2, a n plus 2 plus a n, all proportional to x2 power n, must be 0. Okay? To satisfy the equation.